Hey Ben,
Hey Prof.
we are doing another form of decarboxylation.
Yes, so for this decarboxylation we are doing it in neutral condition.
Neutral, just now we talked about acidic, but now we can do it neutral?
Yes, we can do it in neutral, but the given criteria is that it must be a methoxy group, ester with a methoxy group that's attached.
So we know that ester, just like a carboxylic acid, it must be the terminal group, right?
Yes.
So carbon 1, and we have 1, 3, in which the third carbon is a ketone group, we can do this decarboxylation.
Yes, it's also known as Krachpo decarboxylation.
Krachpo.
Yep. Okay, so the main reagents we'll be using is sodium chloride and wet DMSO.
So this sodium chloride, it must be maybe some solid salt.
Yep, solid salt.
And then we try to dissolve in wet DMSO.
Yep.
Why wet?
Wet is because this DMSO contains water.
And just to recap, DMSO stands for?
Dimethyl sulfoxide.
Right, so sulfoxide and dimethyl, right? Good, and this is a polar
aprotic solvent.
aprotic because there's no protic hydrogen. Okay.
Alright, so I will just draw out how the mechanism look like. So mainly the main thing that is looking here will be the Cl. We need the chloro. So what this chloro can do is that this chloro can attack the methyl group.
The chloride acting as a nucleophile, right?
Yes.
So this is the electrophilic side, and that's because you have a delta plus carbon due to the polarization of a delta minus oxygen.
Yep. So after it attacks, this carbon will have 5 bonds, so this carbon will break its bond, leading to this carbon having 5 bonds, and it doesn't like it, so it will break again.
Oh, it doesn't go up?
Nope, it doesn't go up, it causes it to break.
Right, so you see it forms it, right, it breaks. But it could break this pi bond, right?
Yes, it could.
But what is driving this to break the bond on the left?
Well, even if it breaks in and forms a negative charge, this negative charge will be unstable. If it forms back, it can form a carbon dioxide and leave, which is entropically favorable.
Very good. So it's about the delta S, right? Entropy driven.
Yeah. So I will draw the next intermediate, which is here. It will go up, and the negative charge like that.
Right.
So
enolate.
Yes, but this is not an enol. It's an enolate. So right now, this is where the wet DMSO comes into play. So we know that as a wet DMSO there is a water. So we know that there's a OH.
So there's protonation.
Yes, there's protonation. So this can take and OH. So
Okay.
what we have next is
And the byproduct, right? In our case, we have a methyl chloride, right?
yes, methyl chloride.
Yeah.
As well as a as well as a CO2.
CO2. G. Entropy driven. Okay.
So from here we know that this can eno-keto-tautomerize.
You know what this is? It's wet.
So we know that it can eno-keto-tautomerize and the keto form is more favored, and we can get our final product from decarboxylation.
Right, so this is the neutral way of doing decarboxylation. Some criteria: a terminal ester group, third position ketone.
Yep. Right.
See you.
Bye bye.